This project was funded for the 2008-2009 period, and we were working with the School of Medicine and Dentistry. And the problem we were trying to solve for them was basically they had all these 3D scans of patients. The scan on the slide here is not of a patient; it's actually one of the doctors, or I think it's Lifong's friend, because we can't obviously show patient data. So that's a person who's not really suffering from any medical condition when the scan was taken. The idea over here was to use this data that they had for clinical diagnosis, treatment planning. The main goal that we were trying to do was to help them with post-treatment monitoring. So that the third point there was what we were trying to help them with. So when they had all these scans, their normal way of analysis involved a manual registration of these faces. Registration is a process when you match these two or more scans in alignment, and then you can study the differences between the two scans. So what they were doing is they had a software which helped them manually align these scans. So they had to mark points on the face, and the software would match these points, and then compute the distance between the faces. This is a very classical registration approach here. So as I said, this person is not really suffering from any medical condition. All the areas in green indicate no change, and blue and red are the two ends of the spectrum here. So the positive distance and the negative distance. And these regions of change are not expected because nothing really has changed in the person's forehead. If anything, we expect some changes near the mark region because that's like soft tissue. With some changes in expression, you expect some changes near the mark, but not really on the forehead. So our approach involves, it's a very, very quick overview to let you know what we did. Our approach involved taking two scans. We had an approach to detect landmarks on the face. So this was a very statistical-based model. A common name for this is active shape models or active contours, which are used in image processing a lot. And we use this model to detect these landmarks of the face. So the model usually involves some region of the face, and we try to search. It's more like template matching. So we search for this region on the face, and then we can localize specific regions. So now we know where the eyes are and the nose is, and this is done automatically with no restrictions on initial position of the face or orientation of the face. And the main step we took forward with this research was trying to detect these face points on faces with deformations. So this scan over here, again, is of a doctor, and he's just puffing out the cheek. So he's not really suffering from any swelling or anything there. He just puffed out his cheek, and that's a typical example of the kind of deformations that we face with our patient data. So it's quite serious swellings or quite serious bone growth or deformities in the jaw. And we would like to detect these points in the presence of these deformities. So one of the things we achieved with this project was actually detecting these points in the presence of quite serious facial deformities. Once we have these points, we could register the faces using these points. And then we had another step where we detect stable regions. In this application, the stable regions would be around the eyebrows or the forehead, because the work they were doing was mainly maxillofacial surgery. So we know that they're working on the lower half of the face. We know the upper half of the face, and especially the forehead and the eyebrows, which is quite bony, very bony area with less soft tissue, is quite stable to use for the matching. So we know that region is stable. We use that region to perform a very fine alignment of the faces, which happens there. And then we compute the distance between these two faces. So when we do that, what we get is a much more accurate depiction or estimation of the actual variation between these two faces. So now we see in this example, regions around the forehead and the eyes have not really changed. So it's zero distance on the map, and so we know that this region has not changed, and this conforms with what we know of the person. So the blue region there is a positive change, while the red region is a negative change, and we know, because we know the data, that that's a very accurate result. So going back to the first achievement of this project was to improve the accuracy of the results. So the points in blue there, the points in green there are the detection results while we were working on this project. So this project really ties in with what I was doing earlier with my own PhD research. So I try to detect points on the face to do face recognition. And since data was completely different from data that I'm using, I had to change the algorithm a bit to work with patient data. So the first achievement was getting better accuracy. Once again, I can't show the faces where there were quite serious deformities, where the accuracy improved quite substantially. But this example here, there's a bit of error there on the eyebrow, but the regions we're interested in were the nose and the eyes specifically. So we can see the nose area, especially the nose tip point right there, is much more accurate. And while it seems like it's a very small improvement in the actual location there, it's very substantial in the sense, if you need measurements of these locations, so you need a measurement between the nose and the eyes, that would be actually quite significant. That small improvement in accuracy right there. So that was, research-wise, the main achievement that we made. So with these points, this is an example now. So the same example I showed you earlier on the first slide. Now with the registration approach that we applied, there's only a change on the eyes, which is true because the person has eyes open in one instance and eyes closed to the next one. So now there's only changes near the eye. There's changes on the periphery of the scan because there's outliers there, and it's different between the two scans. But the face region has not changed at all. A bit of change near the mouth because, like I said, it's soft tissue there, so it's quite expected with a slightly different expression. The second achievement was to put all of this together in a software, which we provided the hospital. So now, this software was much more user-friendly than the software they were using earlier. The other achievement was we had a lot of facility for user feedback. So this helps us gather more information about these scans from the actual clinician or the doctor. So this data, this software really helped ease the burden on the clinicians who are doing this work. And this feedback mechanism was good for us, where we can get back feedback. We can get feedback on the data and on the analysis that they were doing. So all of this, in the end, the main achievement was this collaboration that we established between the School of Medicine and Dentistry and us. And like I said, this is just trying to give them a tool to analyze data before and after surgery. There are things we could do there to improve this tool. But as far as research is concerned, the main thing was we identified much more interesting projects that can be developed later. And one of the things that really excited me and Andrea was how we can detect conditions from patients before we know that they have it. Something like Down syndrome there is actually quite obvious, even for an untrained eye. So if you meet a child with Down syndrome, even for an untrained eye, you know that there's some abnormality in the facial structure. But something like schizophrenia, you could really never know. In most cases, you wouldn't know until you observe them. And I have found out that you can actually measure distances between feature points of the face and detect that this person is quite likely to have schizophrenia, or quite likely to develop schizophrenia in the future. And that is something that I would be really interested in working in.
Thank you, Prathap.